Now we're going to talk about Taylor series. Since we're talking about series and local behavior for complex numbers. In the last video, we had considered series, power series. Yeah, we looked at power series and we saw things like radius of convergence and all of that. So Taylor series here. So a Taylor series expresses a function as an infinite sum of derivatives at a point A. So it expresses a function as an infinite sum of derivatives at a point A. So we have f of x equals summation from n equals 0 to infinity of the nth derivative of f evaluated at a all over n factorial multiplied by, into x minus a raised to power n. So f n of a is the nth derivative evaluated at a, like I said, and n factorial is the factorial. So that's the Taylor series definition. But then, very closely related to the Taylor series is Maclaurin series, which kind of simplifies the Taylor series. So here, a now is like the point about which we are taking the series. But if A is 0, then we now have the Taylor series. So simply, Maclaurin series is Taylor series when A is equal to 0, right? So f of x now in that case becomes f of n, the nth derivative of f evaluated at 0, then x minus a now becomes just x because a is 0. So x raised to power n over n factorial there. This is called the Maclaurin series. So for analytic functions now, a function is analytic at a point if it is infinitely differentiable. And of course, that has certain implications. Part of it is that it obeys the obeys the Cauchy-Riemann equations and all of that. And of course, if a function is also analytic, it means that its integral along a closed path is 0 and all of that. So another thing here is that its Taylor series converges to the function near that point. So examples include e raised power x, sine x, and cos x, exponential functions like given functions like sin x and cosine x, and we have polynomials in general. Another example will be the absolute value of x at x equals 0. So this doesn't work in that case. The absolute value of x will not be analytic because x is equal to 0. But at x equals 0, it is not analytic. Now we talk about polynomial approximation ideas. Now, one powerful thing uh, the Taylor series has done for us is that you can now express what the functions known as transcendental functions, right? Generally speaking, we have polynomial functions and transcendental functions. We know polynomials, right? Like things that are not expressions that are added together with increasing powers. The powers are always whole numbers, no fraction, no negatives. But then we have transcendental functions like sine, cos, log, trig, all of these things. But with the help of Taylor series, we can express such transcendental functions like sine x, e raised power x, cos x, and all of that. We can approximate them as polynomials. So Taylor series builds approximations like f of x is approximately f of a plus f prime of a into x minus a plus f prime prime of a evaluated at a, f prime prime of a rather, over 2 factorial x minus a squared and so on and so forth. So adding more terms improves accuracy. So since the Taylor series is only helping us to get approximate polynomials to express transcendental functions, the more terms you have in your series, the more accurate the solution, the approximation gets. So, but at best, it will always be an approximation. For instance, we have all these ones. For exponential function, right? You have e raised power x equals summation from x equals n equals 0 to infinity, x raised power n over n factorial. Now you may be wondering, how did we get here? So, okay. Okay, I mean, I think that largely the expressions we have here are basically, Maclaurin series where a is taken to be 0. So I'll use the exponential function to see how we actually arrived at this expression so you understand what exactly we are talking about. So we said it already that the Maclaurin series is given as f of x, which is approximately f of 0 plus f prime of 0 all over 1 factorial, one derivative, then x raised power 1, then plus f prime prime of 0 all over 2 factorial, x raised power 2, and so on and so forth. So if we now have If you then have f of x, okay, I guess I want to switch over here. If we then have f of x is e raised power x, what do we do? It means we need to find, first of all, we need to evaluate f of 0. F of 0 is e raised power 0, which is 1. That's first thing. Then now we have f prime of 0. F prime of 0 means we differentiate e raised power x. That will still be e raised power x, and e raised power x at 0. That's also 1. Then f prime prime of 0, that's second derivative. So maybe this is even good. So I say f prime of x, f prime of x is e raised power x again. F prime prime of x is still e raised power x. And f prime 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 of x is still e raised power x. So it's one of the easier cases. So, and as you evaluate at 0 for each one, e raised power 0 is still 1. F prime 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 of 0 is also e raised power 0, which is equal to 1. So at the end of the day, what you have is that e raised power x can then be approximated to be f prime of 0, that is 1. Okay, let me write it out. So that's it. So you have f prime of 0 plus f prime of 0 all over 1 factorial x raised power 1 plus f prime prime of 0 over 2 factorial x raised power 2 plus f prime 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 of 0 over 3 factorial plus all of that. Okay? So if you then put it together, so e raised power x is approximately f prime of 0. You know, already all of this is 1 each, right? So that is taken care of. We just take care of other things. So we have 1 plus 1 over 1 factorial. So that's 1 over 1 factorial x plus 1 over 2 factorial x squared plus 1 over 3 factorial. Okay, I skipped x cube here. 1 over 3 factorial x cubed plus all that. So that's x cubed here plus all of this. So we have e raised power x to be approximately 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus all of this. So that tells us that e raised power x is approximately, if you look at this, then that's like summation. Okay, I think we can now say e raised power x. Well, it's approximately a summation from n equals 0 to infinity of x raised power n all over n factorial. You know, because now when n is 0, we have x raised power 0, 0 fact all over 0 factorial. X raised power 0 is 1, 0 factorial is 1. So 1 over 1 is 1. Next, when n is 1, we have x raised power 1 all over 1 factorial. 1 factorial is 1, we have x. At 2, we have x raised power 2 all over 2 factorial. That's what we have here. And that's why we have this kind of expression like that. Probably in the practice problems, we'll be doing something close to this again. So it's the same approach for sine, for cosine. Um, I don't know. Maybe we are going to let's hope that in the practice problem we'll see how this plays out. For geometric series, I've already done this before. You know, okay, well, maybe I should do it again here. Is it necessary? Is it necessary? Is it necessary? Okay. Yeah, I think I want to leave that. Let's go on. So you have 1 over 1 minus x equals summation from n equals 0 to infinity, x raised power n. So where we have absolute value of x is less than 1. The radius of convergence, of course, is 1 here. So example 1 now, want to expand e raised power x. Oh, that was what I did there. So since all derivatives of e raised power x are e raised power x, then we simply have this. That's what I just finished doing. Then for expand ln 1 plus 1 plus x. So ln 1 plus x can be given as this whole expression. Okay, maybe I should do, let me talk about ln 1 plus x, right? So now we have f of x. Okay, is it Maclaurin? If it's Maclaurin, we'll be expanding about something. So we just do Taylor's, yeah? Expand ln 1 plus x. So here now we have f of x equals ln 1 plus x. Okay, I don't want to deal with. So the first thing you want to do is find as many derivatives as possible. So you have f prime of x. When you differentiate ln 1 plus x, to differentiate a logarithmic function, right? You want to do is differentiate the expression, you have 1, and put it over the original. That's 1 plus x. Okay, so 1 over 1 plus x, that's what that's going to give us. And then, of course, that's the same thing as having 1 plus x raised power minus 1. So that's easier for other derivatives. So for f prime prime of x now, to differentiate this, we use function of a function. So differentiate, bring down the power, that's -1. Multiply inside, that's one. Sorry, differentiate inside, that's differentiate one, that's constant, that's 0. Differentiate x, you get 1. Then original thing, that's 1 plus x raised power minus, that's 1 plus x raised power -2. So that means f prime prime of x is 1 plus x raised power -2. Okay, minus is outside here too. Then f prime prime of x, that's the third derivative here, is equal to, so again, differentiate this, you have minus is there already, times, bring down the power now, that's -2. Differentiate inside, that's 1. Then the original expression, reduce the power by 1, that's -2 minus 1. So if you put that together, you then have 2, 1 plus x raised power -3. And you can go on and on. Okay, let me do one more derivative. So f, the fourth derivative now, the fourth derivative. So again, you have 2, bring down the power, -3, differentiate inside as 1, then the original expression raised power -3 minus 1, that's -4, and that will give us -6 into 1 plus x raised power -4. Okay, so what does that tell us? You have we have a pattern. This is 1 minus 1, this is 2 minus 6, and it goes on like that. And that is why by the time we put it all together, you'll see the trend that it actually follows this -1 raised power n plus 1, blah blah blah. So let's put that together. So now we then have ln 1 plus x to be approximately f prime of 0 plus f prime prime of, oh, sorry, it's f of 0, first of all, the original expression. So that's f of 0. So it's approximately f of 0 plus f prime of 0 over 1 factorial plus f prime prime of 0 over 2 factorial. Okay, I've also skipped x. So this is x here plus f prime prime of 0 all over 2 factorial x squared plus f prime 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 of 0 all over 3 factorial plus x raised to power 3 plus f prime fiv of 0 over 4 factorial x raised to power 4 plus all of that. So if that is the case, then we know that the length of 1 plus x is approximately f of 0 now. F of 0, that means we need to try that. So f, okay, first of all, f of 0 here is actually lane 1 plus 0. That is lane 1, which is simply 0. And then f prime of 0, that is 1 plus x raised to power -1. So because this is 0 now, so that is simply 1. Then here we have f prime prime of 0, that is minus 1 raised to power -2. So this is simply -1 in short. Then here we have f prime 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 of 0. That is 2 into 1 raised to power -3. That is simply 2. Then next we have -6 into 1 plus. That's fiv of 0. That is -6 into 1 plus 0 raised to power -4. That is simply -6. So we have 1 minus 1, 2 minus 6. So this is f of 0 is 0 from the beginning, right? So f of 0 is 0. So here we have 1 over 1 factorial x. Then f prime of 0 is -1 all over 2 factorial x raised to power 2. Then this one is 2, right? I think that's 2. Yeah. 2 over 3 factorial x raised to power 3. Then the next one is -6. So we have -6 all over 4 factorial x raised to power 4 plus all that. So we can write this to be summation from n equals 0 to infinity of, if you look at the way it's going, the signs are alternate. Okay, let me do one more layer. 0 is gone, right? So 1 over 1 factorial. So we have 1 over 1 factorial. We simply just have x minus 1 over 2 factorial. Or if you like, maybe it makes more sense to have x squared over 2 factorial plus 2 over 3 factorial x raised to power 3 minus 6 over 4 factorial x raised to power 4 plus all that. So we then have that to be approximately summation from n equals, I think n equals 1 to infinity. I think that will be right. N equals 1 to infinity. Yeah, n equals 1 to infinity because the first term is gone. So minus 1 raised to power n plus 1 minus 1 raised to power n plus 1. Okay, I think there's still a simplification I need to do here. Okay, and yeah, I think that'll be important so we can get a total approximation. So in this case, you will notice that this is x minus x squared over x squared over 2 factorial, over 2 in short, all right, minus 2 over 3 factorial is 6, x cubed, minus 6 over 4 factorial is 24, x4, plus all that. Because 4 factorial is 4 times 3 times 2 times 1. That's 24. So I think we can still keep tidying. So lane 1 plus x is still what we are dealing with. So this is x minus x squared over 2 factorial minus 2 here is 1, 2 here is 3. So we have a pattern x cubed over 3, this is plus, right? This is plus here. And so the signs are alternating. Minus 6 here is 1, 6 here is 4. So we have a very nice pattern now. 2 factorial, this is just 2. So plus all of that. So it means we can already guess the next one is going to be x raised to power 5 over 5. So this is approximately now summation from n equals 1 to infinity for minus 1 raised to power n plus 1. That takes care of the alternating signs. So when n is 1, we have minus 1 raised to power 2. So that's why we have x raised to power 2. So this is x over x raised to power n all over n, not n factorial now. So that's why finally we can say that the we can say ln 1 plus x is equal to summation from n equals 1 to infinity minus 1 raised by n plus 1 x raised by n all over n, like that. So that's the general. So normally ln 1 plus x is transcendental, but using Maclaurin or Taylor series now we can then make it into like a polynomial expression as we have here. So and the whenever you have alternating sign, it's always good to have minus 1 raised by n plus 1. So the signs will keep switching over like that. And that is exactly how we came up with this. So for sine x, you can do the same thing. So, sine 0 is 0. So that's why the first term is x here, because that sine 0 part is gone. So the next thing is differentiate sine x, you get cos x. So cos 0 is 1. So that's 1x over x factorial. Then differentiate cos x, you get minus sign. That will go again. So power 2 is gone. Then differentiate minus cos x, you now get minus sine x. That's why this is now negative. And you have power 3. That's why sine x is an odd function. And if you do for cos, cos is an even function. So all the odd terms will disappear. For sine x, because it is an odd function, all the even terms disappear, as you can see here. Right. So we can do this. So for sine x now we have this is symbolic stuff here using sim So x minus x cubed over 6 plus x raised by 5 over 120 and so on and so forth. Then we can also do Python expansion at a point. So expansion at a point is the idea of Taylor series actually. So Maclaurin just simplifies it. If you expand at 0, it makes things a lot easier. But Maclaurin series talks about Taylor series talks about expanding at a given point. So all this expansion we've been doing, they are easier because we're expanding at 0. So imagine you want to approximate the exponential function for Taylor series, and the exact you can see the closeness is very interesting. So I think, okay, I hope if there's no question talking about using the actual Taylor series in the practice problem, I'm going to do it so that you can also see if you're not what if you are not expanding about 0, according to Maclaurin. Then for Taylor, I'll show you that one. So then we have, since we are just using Taylor series to approximate a transcendental function, there's bound to be error. Wherever you stop determines the kind of error you get. So the remainder, of course, the error term of the remainder is Rn of x is f, the n plus one, n plus first derivative, so to speak, evaluated at c all over n plus 1 factorial times x minus a raised by n plus 1. This is the remainder of the expression. So where c lies between a and x, so more terms means smaller error, and this depends on the convergence. So radius of convergence, of course, we've always done this. So Taylor series converges within a radius given as limit as n approaches infinity of an plus 1 over an, absolute value of that. The example, ln 1 plus x converges for absolute value of x less than 1, for instance, based on, since we have now turned it into an expression, maybe I can even do that. Let me do the radius of convergence so you can understand why the radius of convergence is like that. So in this case now, I want to say, I want to find the radius of convergence, to find the radius of convergence. So, you have summation from any, okay, I think I want to make this bigger. So I think I don't need so much space like I used before. Okay, so to find the radius of convergence for lane 1 plus x that we just found, so we remind ourselves of the expression. So lane 1 plus x is approximately summation from n equals 1 to infinity. You have minus 1 raised power n plus 1, x raised power n, all over n, not factorial. So you can rewrite this as summation from n equals 1 to infinity of minus 1 raised power n plus 1, all over n. Then x raised power n is isolated, because at the end of the day, all we need is this part. Okay, that is our an. So we know that an is equal to minus 1 raised power n plus 1 all over n. An plus 1 would then be minus 1 raised power n plus 2. That's n plus 1 plus 1 all over n plus 1 down here. So we now need to, the radius of convergence now would have to be, so we do limit as n approaches infinity for the absolute value of an plus 1 all over an, and that is limit as n approaches infinity for an plus 1, that's minus 1 raised by n plus 2 all over n plus 1 divided by minus 1 raised by n plus 1 all over n, like that. So that gives us limit as n approaches infinity for the absolute value of minus 1 raised by n plus 2 all over n plus 1 times n over minus 1 raised by n plus 1. So we then have limit as n approaches infinity for, so you have minus 1 raised by n plus 2 divided by minus 1 raised by n plus 1, then times n over n plus 1, like this. So I want to get rid of this one first. So we have limit as n approaches infinity of minus 1 raised by n plus 2 minus n plus 1 here times n over n plus 1. So this is limit as n approaches infinity for minus 1 raised by n plus 2 minus n minus 1 times n over n plus 1, like this. So this is limit as n approaches infinity for minus 1, n cancels, and 2 minus 1. So this is just 1 times n over n plus 1. So minus 1 minus 1 raised power 1 is simply minus 1. So limit as n approaches infinity for n over n plus 1. Okay, so in this case, if you substitute directly, you're going to get infinity, but you can actually avoid that by dividing through by n. So you have n over n plus 1 over n. So that is limit as n approaches infinity. Now, I've forgotten about the minus because we are taking absolute value. So because this is minus 1, so the absolute value will just get rid of that. So we then have this to be 1 over 1 plus 1 over n. So if you now substitute infinity, so you have 1 over 1 plus 1 over infinity, which is 1 over 1 plus 0. And that is simply 1 over 1, and that is 1. Okay, so if you now multiply with multiply with absolute value of z, right? So multiply with absolute value of z. So we have 1 times absolute value of z. There's no n here again. So, and we need this to be less than, 1, right? We need this to be less than 1. So that means that if you divide 3 by 1, so absolute value of z is less than 1. So the radius of convergence, is 1. So radius of convergence is equal to 1 because this absolute value of z is less than 1. That's exactly what this explanation is. Okay, we are not using z, we are using x. So this converges for absolute value of x less than 1. So it's not z we are using here, it should be x. So that's absolute value of x, absolute value of x, absolute value of x here. So that's why absolute value of x is less than 1 in that case. All right, so with that out of the way now, we can move on to we can try to finish up. So Taylor series approximates functions locally. Analytic functions equal their Taylor series, and they are widely used in physics, engineering, and numerical methods. Like I promised, if there's no, I'm going to solve 2 for sure. So if there's no Taylor series, I'm going to intentionally use it so you can see the difference between Maclaurin and Taylor's like that. So let's see what we have next in that regard. Okay, I'm solving problems 4 and 10 in this case. Problems 4 and 10. Problem 4, find the Maclaurin series for lane 1 plus x up to x4. Okay, I've done this already, so probably going to take another series in that regard. So I'm supposed to take 4 and 10. What is 10? 10 is find the Taylor series of lane x about x equals 1 up to x minus 1 cube. Exactly. So that's 1. So since so that's so I'll be taking that one, and then I'll be taking, maybe let me look for another one here. Taylor series of root 1 plus x up to x raised to power 4. Root 1 plus x. That's looking like, of course, that one was log, right? But let me see. Okay, I think I'll now do 10 and 16. Find the Maclaurin series of x e raised to power x up to x raised to power 4. Yeah, so yeah, let me do 10 and 16. So the first 10 says find the Taylor series of lane x about x equals 1 up to x minus 1 raised to power 3. So let's see that. Um, so problem 10, we want to find the Taylor series of lane x about x equals 1. So if it was about 0, that's Maclaurin, that's what we're saying. And we want to do that up to x minus 1 raised to power 3. Okay, that's what we want to do here. So step 1, in step 1, you compute derivatives. Compute derivatives. Compute derivatives. So of course, f of x is lane x. F of x is lane x. That means f prime of x is equal to, differentiate lane x, that's 1 over x. Well, okay, well, when I'm done with the derivatives, I'll come back. And since we need it up to power 3, so it means we need to do up to 3 derivatives. So f prime prime of x now, this is for easier differentiation next time. I can take this as x raised to power minus 1. So f prime prime of x is now minus x raised to power minus 2, right? And then, which is, of course, the same thing as minus 1 over x squared. So this one helps me to differentiate better. So f prime prime of x now, differentiate this, we have minus 2. Okay, that will be plus 2 x raised power minus 3, which is 2 over x cubed. So here we kind of have alternating signs. Since we are differentiating, we are doing it about x equals 1. So we also are going to need that. We are going to need f of 1, which is ln 1, and that is 0. We are going to need f prime of 1, which is 1 over 1, and that is 1. We're going to need f prime prime of 1, f prime prime of 1, which is minus 1 over 1 squared, which is minus 1. We're going to need f prime 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 of 1, which is 2 over 1 raised to power 3, and that is 2. So now let's write we apply the Taylor formula. So step 2, apply Taylor formula. Apply Taylor formula. So Taylor formula is simply this, that f of x is equal to f of a, but our a now is 1. So we have f of 1 plus f prime of 1 multiplied by x plus f prime prime of 1 all over 2 factorial, second derivative and all. Oh yeah, I should have done this. So this is f of 1, then f prime of a all over, multiplied by x minus 1, because I'm doing it about x equals 1, then plus f prime prime of 1 all over 2 factorial x minus 1 squared plus f prime 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 of 1 all over 3 factorial x minus 1 raised to power 3 plus all of that. So in this case, we then have then we can then fix up the values. So f of x now is equal to f of 1, all has been done. F of 1 is 0. So we're going to lose that term because it's 0 already. So this is 0 plus f prime of 1, f prime of 1, that is 1. So we have 1 multiplied by x minus 1. F prime prime of 1, f prime prime of 1 is actually minus 1. So we have minus 1 all over 2 factorial x minus 1 squared plus f prime prime, f prime 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 of 1. That's the third derivative evaluated at 1. That gives 2. So we have 2. So we have 2 over 3 factorial x minus 1 raised by 3 plus all that. So it means that f of x now is equal to 1 times that's x minus 1, then minus, that's minus 1 over 2. 2 factorial is 2, by the way. So that'll be, or yeah, so that'll be 2 factorial, that's 2 x minus 1 squared plus 2, 3 factorial is 6, that's 3 times 2 times 1, 6, and x minus 1 raised by 3 plus all that. So we can find a pattern here already. We can already find a pattern. You see that f of x is equal to x minus 1 minus 1 over 2 x minus 1 squared plus 2 here is 1. So we have 1 over 3 x minus 1 raised by 3 plus all that. Then f of x now is equal to x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed all over 3 and all that. So we can try to, we can generalize, right? So I can just say overall, f of x, which is ln x, f of x now, which is equal to ln x, can be said to be approximately um, x minus 1, x minus 1 minus x minus 1 squared all over 2 plus x minus 1 cube all over 3 and so on and so forth. So that's like summation from n equals 1, because the first term is gone to infinity, of minus 1 raised power n plus 1, because we have alternating signs. Anytime you have alternating sign, you can have minus 1 raised power n plus 1 into x minus 1 raised to power n, okay, all over raised power n, right? Yes, all over n. Yes, all over n. I think that works. So At n equals 0, we have minus 1 raised to power 1. At n equals 1, right? At n equals 1, we have minus 1 raised to power 2. That will be positive. And then we have x minus 1 raised to power 1. At 2, we have minus 1 raised to power 3. That's negative sign here. Then we have x minus 1 squared over 2. Yeah, so this is like how to approximate that. So the second question I'll be taking is question 16. So question 16 says, question 16, find the Maclaurin series of x e raised to power x up to x4. Okay, x e raised to power x up to x4. To find the Maclaurin series, that's problem 16. Problem 16. To find the Maclaurin series of x up to x raised to power 4, what do we do? So here now we know that we have f of x to be x e raised to power x. This is not so easy, but we have to do product rule every step of the way. But no worries, we go for it. So f of x, right? This is f of x. And for Maclaurin series, it makes life easy. We just know they're going to, okay, let's even do all the derivatives first. So let me do f prime of x, first derivative. That's product rule. That is u. This is u, this is v. So I have u dv dx. Differentiate this now plus v du dx. Yeah, that's that. And that means we have x e raised to power x, u dv dx plus v. So that's e raised to power x like that. So we have so that means we have e raised to power x into x plus 1. That's the first derivative. So it's up to x raised to power 4, so we need to differentiate 4 times. Second derivative, f prime prime of x now. So now we have u and v. So we have u dv dx plus v du dx like this. So that means we have e raised to power x plus x e raised to power x plus e raised to power x like that. Is that correct? I think so, yeah. Yeah. U dv dx, differentiate this, you get 1. Then v du dx, we get this. So now we have e raised to power x into, okay, well, we can still tidy this up. So this is x e raised to power x plus 2 e raised to power x. So we have e raised to power x into x plus 2. Okay, I think I'm seeing a pattern here. Let's see if the pattern is always true. Then what do we have next? We have f, the third derivative of x now. That is u dv dx plus v du dx. Okay, I think the pattern is true always. So we have e raised to power x into, e raised to power x, plus x plus 2, e raised to power x. So yeah, so we then have e raised to power x is common into 1 plus x plus 2. So that means, oh yeah, the pattern is correct. That's e raised to power x into x plus 3. Then we do the fourth one because we are going as far as x raised to power 4. So we have fiv of x. That's the fourth derivative. That's u dv dx. Oh yeah, u dv dx, differentiate x plus 3. We get 1 again. Plus v, which is x plus 3, du dx. That's e raised to power x. So in short, from the pattern, we know this is going to be e raised to power x into x plus 4. So having done all of that now, we need to now evaluate at 0 for Maclaurin. Okay, so let's go for that. Okay, so we now need, first of all, we need f of 0. That is simply 0 e raised power 0. That's 0. We have that. Then coming here now, we need f prime of 0. So f prime of 0, that is e raised power 0 into 0 plus 1. That is 1 in short, because this is e raised power 0. That will be 1. Yeah, that's 1. So we have 1 here. Then next, we have, I think we always have the, so here we have f prime prime of 0. That is e raised power 0 into 0 plus 2. Did I do the last one right? Yeah, that's 1. So this one will now be 2. This is 2 because e raised power 0 is 1. 0 plus 2 is 2. 2 times 1, 2. Okay, I guess the next one will just be 3. So this f prime prime of 0, which will be e raised power 0 into 0 plus 3. So this one will be 3. Okay, I see the pattern coming out already. So fiv of 0, that is e raised power 0, 0 plus 4. And of course, that will be 0 at last. So we can write out the formula now. So f of x, which is equal to e raised power x, e raised power x, right? X e raised power x, x e raised power x is approximately, so Maclaurin series, that's f of 0 plus f prime of 0 x plus f prime prime of 0 x squared all over 2 factorial. Okay, we still have 2 derivatives to go. So we have plus f prime 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 of 0 all over 3 factorial x cubed plus f iv of 0 over 4 factorial x raised power 4, and so on and so forth. So we are going to x raised power 4. So we've seen already that f of 0 is 0, straight up, x raised power x. So that's 0. So that means that x raised power x is approximately 0 plus f prime of 0 is 1. So we have 1x plus f prime prime of 0 is 2 over 2 factorial x squared. F prime prime prime, that's 3 over 3 factorial x cubed. Then fourth derivative, that's 4 over 4 factorial x raised power 4 plus all that. So in that case now, we can say x raised power x is approximately x plus 2, 2 over 2 factorial, that's 2 over 2 x squared, 3 over 3 factorial, that's 3 over 6 x cubed, 4 over 4 factorial, that's 4 over 24, 4 over 24 x raised power 4 plus all that. Then we can tidy up a little bit more. X raised power x is approximately x plus x squared plus 1 over 2 x cubed, 1 over 2 x cubed plus 1 over 6 x raised power 4 plus all that. What sense can I make of this? I think this is I think leaving it up here is a better pattern. Yeah, leaving it up here should be a better pattern. Not simplifying, because I can easily generalize like this, I suspect. So let me remove this. We could leave it like this, right? But I want to be able to write a general expression for it. That can help us to find the radius of convergence if we need to, you know. So this is not wrong, but I want to be able to write the general expression. So this looks like I can generalize better like this. So we have x plus 2 over 2 factorial x squared plus 3 over 3 factorial x raised to power 4 plus 4 over 4 factorial x raised to power 3, sorry. Then x raised to power 4, right? And so on. So okay. Okay, I think I'll still get it. That's fine. So x is now approximately, so we can then write summation from n equals 1 to infinity of, I can already see n over n factorial x raised to power n. Yeah. So, but interestingly, this can simplify it. So x is approximately summation from n equals 1 to infinity for, so this is n over n over n factorial. That's like n times n minus 1 factorial x raised to power n. Yeah, so n can cancel out. So yeah, this is even cool. So x is approximately summation from n equals 1 to infinity. X raised to power n all over n minus 1 factorial. Yes. So now to get all that out, so when n is 1, we have x raised to power 1 all over 0 factorial. Yes. When n is 2, we have when n is 2, we have x squared all over, because this is going to be 2, x squared all over 2 factorial, which is 2. When it is 3, right, we have when it is 3, we have, that's why the other part it was going to be fine too. When it's 3, we have x cubed all over 2 factorial. Yeah. So it's like we can as well write it as this. X is equal to, if you want to write that expression in the long form, so it could still be written as, okay, when did I turn it to x? No, it shouldn't be x, it's x e raised to power x. Yeah, so x e raised to power x, x e raised to power x, x e raised to power x, x e raised to power x. So we are saying that in that series form, x raised by x can finally be something like this now. So if I want to expand, I have, when n is 1, I have x raised to power 1 all over 1 minus 1 factorial plus x raised to power 2 minus 1 all over, 2 minus 1 factorial plus x raised to power 3 all over 3 minus 1 factorial, x raised to power 4 all over 4 minus 1 factorial, and so on and so forth, so that we then have that to be approximately x all over 0 factorial plus x squared all over 1 factorial plus x cubed all over 2 factorial plus x4 all over 3 factorial. So we have the factorial is lagging one step behind. So that makes sense. So we have then x all over 0 factorial is that. So x over x squared plus x cubed over 2 factorial plus x4 over 3 factorial plus all that. And that makes sense, right? Because normally, we have so check, right? We already know we have x e raised to power x, and we know that this is equal to x e raised e raised to power x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial, and so on and so forth. So if we expand, e raised to power x is already all this. So if we expand, we just have x plus x squared plus x3 over 2 factorial plus x4 over 4 factorial plus x5 over 4 x3 or x4 over 3 factorial. Yeah, 3 factorial, x5 over 5 factorial. Yeah, so that actually confirms the reality. So with that, we come to the end of this interesting video about the Taylor series and by extension, the Maclaurin series. So don't forget to try out the 20 questions. You have the first 10 showing up here. I've done 10 and 16. Then you have 11 to 20 showing up here. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to the channel already, I thank you very much for doing that. And if you haven't subscribed, why not go ahead right now, subscribe and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can become a member of the channel by clicking on join. That gives you special privileges like getting to see some videos first or getting to see some videos exclusively, and so on and so forth. So ultimately, don't forget to comment, like, share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.